Okay, one thing is that you shouldn't click on private chat box. You don't use only public chat box for this lab. Yeah. All right. So this is a lab that we're gonna do today. We're gonna first let's so this is the states of matter basics lab. I'll make the link available for you guys. You can download it. In some cases you can also use it in a browser. I usually just download it. It's much more easier. I can use it whenever I want, and it doesn't use my bandwidth. Yeah. So you can download. This is freely available, these labs. And what it is basically you have a container. Yeah, you can see inside the container, and you can see that it has some particles in it. Yeah, it has different atoms or molecules which you can change. In this case, neon has been selected. You can change it to argon or oxygen or water depending upon what you want. Yeah, and you can change the state of whatever inside this container. You can also use heat, but we're not going to use that for now. There is also a thermometer here. You can read the temperature. It gives you the temperature of whatever it is inside. Okay, so using these labs we'll try to understand um, what what happens when you change the state of the matter. What are the changes you should be expecting, what are the changes you should be noting. Okay, and we're gonna learn about different states of matter and about different matters. Okay, so first we'll start with argon. So we'll change the molecule to argon. Yeah. um, Anytime you mess up, you can always click on reset. It will go to the first page, and then you'll have to go from there. Okay, now once we change it to argon, make it to solid. Okay, click on solid just in case, and make sure that whenever you click on solid, it basically goes to the center of the container. So the solid. All right. Okay, so make sure that you click on solid, and what I want you to notice is what is each particle representing here. What is each particle representing here? Is that liquid, solid? It's a solid, obviously, but each particle represent argon, correct? Argon is an atom. Yes. So what we can say is whatever in there is a monoatomic particle, is a solid. Yes. Yes, guys. All right. So so we can. So what do you see about the shape? Is it fixed? Reasonably fixed? Yes. The shape is reasonably fixed. Is there a gap in the particle? Remember that this is a solid state. Yeah, this is a solid state. Is there a gap in the particles? There is some gap, no? It's not a huge gap, but there is some gap. Yeah, not much gap, but there is a gap. Yes, yes or no? Is each particle vibrating? I don't know. Some of you probably will be able to see it depending upon the lag of the internet connection, but you should be able to see that the particles all particles are moving. The particles that are on the periphery are probably moving much more faster than the ones that are inside, but you should be able to see that the particles are in fact moving. Okay, so what does that tell us? That the particle, even in solid phase, can move. Yes. Note the temperature. It's 43 Kelvin. Yeah, and so this is argon is a gas under ordinary temperature, ordinary pressure. Obviously, so if you want it to be a solid, you're gonna have to decrease the temperature a lot. So that's why the temperature is much lower. Yeah. Now if we let's change from solid to liquid. Okay, I'll do that. What I want you to notice is what happens to these particles? Do they change? Okay, if right now they are, they are spherical and pinkish, yeah, do they change in shape? Do they change in color? Second thing I want you to notice is what happens to the space between the particles. Okay, is does the space increase between the particles or decrease? Second is what happens to the vibration or motion of the particles. Yeah, clearly in this particular state you can see that they are vibrating, but if I change it to liquid, see what happens to the vibration. And finally, the most important thing is notice to what happens to the temperature. Yeah, what do you think is going to happen if I change from solid to liquid state? What do you think will happen to the temperature? Will it remain same, increase or decrease? Yep, it should increase. Yeah, and so let's see if we get that. So here you go, I'm changing from solid to liquid. Yeah, and you can see, is there any change in the particle? Is there any change in the particle? No, the particles are same. Yes, they are still argon particles. Doesn't matter if it's a solid or a liquid, it is still an argon particle. Yeah, there is no change in the shape, size or color of the particle. That means that that the particles are same. What happens to the spaces between the particles? Has it increased or decreased? Clearly increased. The spaces between the particles increased. Okay, um, what happened to the motion of the particles? Are the particles are the particles vibrating much more rapidly, much more faster or slower? What do you think about the motion? Is it faster or slower? They are definitely vibrating much more faster. What happened to the temperature? It went up. Yes, when we change the state from solid to liquid, the temperature went up. There are some particles you can see that they escape. Yes, this is evaporation. Some particles escape. Now in this, because they are in the container, they will eventually come back and join the other particles, but some particles will always escape, and if if you didn't had a container, they will go and vanish. And that is how basically, if you leave water out at even at some temperature, or even at low temperature, the water will eventually evaporate, because some particles will escape from the liquid phase, not from the solid phase but from the liquid state. Now can we say that, so we have, this is the solid phase, this is the liquid phase. Yeah, what do you think is, in which state the particles are more strongly attracted to each other? Solid state, definitely solid state. Yeah, the particles are much more strongly attracted in this solid state, and that's the reason why the particles don't move as much, they don't escape. Yeah, they don't leave this particular formation. Yeah, each particle has a specific position and it is surrounded by specific particles, and in pretty much all cases you will see that they don't change their position. Their neighbors are always going to be same. Okay, they don't change their neighbor. Yeah, but in liquid phase the particles are not fixed, the position is not fixed. You can see that particles are changing their neighbors, and they will squeeze into some other some other neighborhood, and so on and so forth. They are definitely moving much more faster. um, so you can see that the temperature is increasing. We see that, so let's focus on motion of the particles and temperature. These are the two things that you need to focus. Here is the motion of the particles. Less motion, less temperature. Okay, and here's a liquid phase, much motion, higher temperature. Yes, can we say that if we decrease the temperature, the motion of the particles should decrease? Okay. Can we say that if we increase the temperature, the motion of the particles should increase? Yeah. So let's change that. Okay, let's change. We can do that. Yeah, we can increase the temperature simply by heating, uh, but we'll simply go and click on the gas phase, and obviously you will see that the motion changes, the temperature basically goes up much higher. Yeah, and so you'll see so this is the gas phase in the container, and so you can see that the particles are there is no connection between the particles. Yeah. What do you think about the intermolecular or interatomic forces in between these three phases? Which has the least interatomic attraction? Solid, liquid, or gas? Gas has the least interatomic attraction. We can clearly see that the particles are moving much more rapidly. In this case, they are they're bombarding with other particles, they are bombarding with the wall of the container. Yes. What type of motion is this? Is this a vibrational motion, translational motion? You don't see that the particles are vibrating. Yes, this is basically because you can see that here. You can see that in solid state, um, no, keep it open, Sneha. Alright, so that's the solid state. You can see that in the solid state the particles are vibrating. Okay, they cannot escape. There is some energy, they have some energy in them. Yeah, but they cannot escape, and as a result they can simply vibrate even in the solid state. Okay, even at such a low temperature. In gaseous state, sorry, in liquid state, you can see that they are vibrating, they are moving. Yes, you can see that they are moving. We don't see if they are spinning, but we do see that they are moving. Yes, so there is definitely two types of motion in these particles, and then we go to gas phase and we can see that they are moving. We don't see that they are vibrating, but they are definitely moving from place to place. Yeah, so we see that as we go from solid to liquid to gas, the moment of the particles increases. Yeah, they are moving much more faster. At the same time, you see that the temperature goes up. Yeah, is that clear? Yes. All right, that's pretty good. Now let's change it to water. Okay, and make it solid. Okay, so we change it to water and make it solid. This is a solid state of water. You can see this amount of space it has. Yeah, I can see that it has this much of space. Yeah, uh, you can see that they are vibrating. Yes, they are not moving, and this is what we saw with argon. The same thing applies even with water. You can see the temperature is low. This is a solid state of water, that is it is an ice. Yeah, let's change it to liquid phase. Again, you can do that, simply change the temperature. If you heat it, you'll see the rise in temperature, and so if you can see the when you heat it, you can see the rise in temperature. You can also see that the motion of the particle increases. Okay, so you can achieve the same results. You can see that it is pretty much almost to the liquid. When you heat it even more, it changes to liquid. Now what type of motion do you see? They are vibrating. Yes. They are rotating. Yes. They are moving a little bit, not by much, but they are definitely vibrating, and they are definitely rotating. Yes. Some of the particles escape. Yeah, that's evaporation, that's normal. You can see that this particle has escaped, but most of the particles are in there. They are there. Yes, you can see that the temperature again has increased. Yeah, as the motion of the particle increases, the temperature increases. There is a clear connection between the motion of the particles and the temperature. Yeah, temperature is directly related to the motion of the particles, and we can see that if we click on the gas button. And so here we see, can see that the particles are rotating and moving. They are not vibrating in this particular instance. Yeah, so when the particles are in gas phase, they don't vibrate, they rotate, because they collide with different particles at different angles, so they will rotate and they move from one place to other place. If you focus on any single particle, what you will see that it pretty much goes into one straight direction until it collides with another particle or with the wall of the container. Yes, you can clearly see that the temperature is up because the motion has increased. Can we say that the motion of the particle is directly related to the temperature of the particles, temperature of the matter? Okay, now what I'll do is I will decrease the temperature and see if we can reverse the process. Okay, I'll decrease the temperature. This is in gas phase, so obviously the temperature, the motion of the particle should decrease. Okay, and so you can see that they are becoming slower. Yes, you can see that they are becoming slower and slower, and they at some point they will collapse into liquid. So this is a liquid state of water. Yes, this is a liquid state of water, and if we decrease the temperature even more, we should see that they would form a specific state. Okay, and this is ice. This is ice. You can lower the temperature whatever you want. And so if you take the temperature even lower, let's see, do you see that so now the temperature is pretty low, so let's keep it like that. Do you see that the particles are moving very slowly? What do you think if we take the temperature to absolute zero, to negative 273 degrees Celsius? What do you think should happen if we take the temperature to absolute zero? Any guesses? Exactly, there will be no motion. Let's do that. Yeah, so let's go pull down the temperature even more. You can see that they are decreasing. Yeah, so obviously you can see that they are not moving at all. And so it gets very difficult to take the temperature to, we have reached the point of very close to the absolute zero, but we can't reach absolute zero. This is zero. I have not paused the screen. Okay, you can see that the particles are in standstill, as if they are, somebody said freeze, and they're freezed. That's absolute zero. All the particles in the world ceases to move at absolute zero. Is that clear? All the particles in the world, all the matter do not move in the matter, all the particles in the matter do not move at absolute zero. That is, absolute zero is the limit of lower temperature. Okay, that's why. So whenever you use absolute zero in chemistry, very close to absolute zero, but not exactly absolute zero, because again, it's practically not possible. But theoretically it is, but practically it is not possible because of there is a always a heat. But there have been temperature 99.9%, I think 99 uh, up to 99% close to absolute zero has been achieved. Very close to absolute zero. I think you know if point 1 degree higher than absolute zero, something like that, where some of the gases just stop to move. um, so that's absolute zero. Okay. um, so let's change our lab to different lab. um, One more thing, I think let's just use this one thing. Okay, so let's talk about argon in a solid state and argon in liquid state. Okay, which do you think has higher density? Density is mass by volume. Yes, so mass is same, obviously mass is same. The volume, what happens, it increases from solid to liquid. So you can see that obviously solid has, that is correct, so solid has higher density. Let's talk about water. Yeah, see, try to imagine imaginary circle of that size. All right, now let's change that to, so let's, I pause the screen. Yeah, now the particles are not moving essentially. So that's ice at um, you know in ice, basically that's has but this kind of specific volume. I'm going to change it to liquid and try to see what happens to the volume. Does it increase or decrease? Okay, so that's motion. What do you think? This is solid. Yeah, this is liquid. What do you think is happening to the volume? Has it increased or decreased? One way to see is that you can see that in ice you can see that there are large spaces between the molecules. Yes, there are large spaces you can see in between this because of the type of bonding that water makes. In liquid, those large spaces are not there, so essentially the volume decreases in liquid water. Okay, and this is the reason why ice has higher density, sorry, not higher, this is the reason why ice has lower density than water. Is that clear? Okay, obviously you can see that that this is argon. So argon, this is monoatomic particle, yeah, so matter, and so this is each argon is made up of one argon atom only. If you take water, you can see that each water molecule is made up of one oxygen and two hydrogen. Okay, so this is molecular liquid, you can say, or molecular solid or molecular gas. Whereas same thing with argon, if you talk about, this is in gas state, this is molecular gas. If you talk about water in gas state, this is molecular gas. Okay, that is the difference between atomic and molecular. It doesn't matter if it's a molecule or atom. The properties of the gas or liquid or solid remains the same. Okay, as you increase the temperature, the motion of the particle increases. Okay, at absolute zero all motion stops. That is the bottom line. Alright, so this is the end of first lab, so we'll go and do the second lab. So I think that's the second lab. Let me see what we need to do. States of matter. Give me 1 second, yeah. So this is states of matter lab. This is slightly different lab. It pretty much has slightly more advanced features, yeah, but it's more or less the same lab. So here again, let's select neon as um, as our material, as atoms or molecules. Okay, we change the state to solid. All right, and again we can see that each sphere is vibrating. Okay, now we'll increase the heat till it becomes liquid. So I'm going to increase the, you can see the temperature is increasing, and see the particles are vibrating much more faster. Yes, so at some point at this particular temperature you can see that it has become liquid. Some particles are evaporating. Yeah, so this has become liquid. You can see the particles are moving much more faster. Now uh, we can crank up the temperature a little bit more, and you can see that some of the particles start to escape. Yeah, and at particular temperature, let's say about 75, the particles will pretty much be free of each other. Yeah, most of the particles will be free. So you can see that about 70 or 75 degrees Celsius, they become pretty much free. So now you can see that clearly, as the motion of the particles increases, the temperature increases as well. Okay, all right. So if we increase keep on increasing the temperature, what do you think will happen at uh, so can we, let's do that. Yeah, just keep on increasing the temperature. All right, so let's go to something like 120. Can we say that the temperatures, the particles are moving much more faster than earlier case? Let's take it to, I don't know, much higher, something about, maybe take it to 500 or so. This is not as fast as I had expected, but let's crank up the temperature to, I wish there was faster way to. No, Arjun, it won't turn to plasma. We are heating the container basically, not the gas itself directly. Yeah, if you use a high temperature flame and heat the gas directly, then it may turn to plasma. You keep doing that, I guess. Okay, so temperature is increasing. You can see the particles are moving much faster. um, okay, we can see that the particles, we don't see that they are actually moving, and we don't see that they are rotating, but we know from the previous experiment that they are also rotating. Yeah, uh, they are not vibrating obviously, but they are moving. That moment is called as translational motion. Yeah, because they're changing their position, and therefore it is called as translational motion. And so this is, increase it. So you can go ahead and increase it, and we'll see what happens towards the end. Okay, I will leave that as a suspense to you guys. Okay, um, there you go. Boom. Yes, that's what I was hoping. What happened? The pressure become too much. Yes, as so can we say that temperature, um, pressure, moment of the particles, all these are related? Yes, can we say that if you had in let's start with the gas phase. Yeah, oops, let's start with the reset and gas phase. If we had more particles, that would exert more pressure on the container. Yes, if we had lower temperature, then there would be lower pressure. Yes, if we had more temperature, then that would definitely be more pressure. Yeah, temperature and pressure are directly related. Yes, that is the reason why you are asked not to keep the gas cylinder that you the cooking gas cylinder near heat, because it might explode. Okay, as the temperature increases, the pressure increases, and you may have a problem. All right, so this is called as kinetic theory of gases. Yeah, um, these factors are all interrelated with each other. Okay. um, all right, let's close this one and let's start with another lab. This is called as build an atom. Yeah, you can build atom using these labs. Okay, so let's let's build an atom. So you have, oops, so let's reset it all. Yes, I want to do the reset. All right, so this is the central. You have a nucleus. At the cross you can add electrons near here, okay, on the orbits. Okay, so you have protons, neutrons, and electrons. Obviously protons and neutrons will go to the nucleus and electrons will go to the periphery, okay, on these orbits. So let's add one proton. Alright, you can see that it is hydrogen ion. You get selected, yeah, on this periodic table. It has +1 charge because it has no electron. Yeah, it has one proton. There is no electron to balance this charge, and therefore it is hydrogen. Alright, we add, let's say, so to balance this positive charge we add electrons. Let's add electron. You can see where it goes into the inner orbital, okay, not to the outer orbital. Alright, we can also select cloud if you want, but it doesn't this is the actual picture of it, and this is you will learn in quantum mechanics next year, quantum chemistry. But you know, for now we'll just stick with the orbitals. Much more easier model to understand. Okay, there are different models of atom. This is the easiest one. Now let's add another. So when we add, basically we know that we need to add, so to make a neutral atom we'll need to add proton and electrons together, right? Because you know, number of protons is equal to number of electrons in a neutral atom. Sneha, yes, that is correct. I just didn't saw your question earlier. That is the that is the gas law. Basically, it explains the gas law. The gas law is, we'll learn about the gas laws later on. But yes, that explains the gas laws. Okay. So let's do that. We'll add another proton and electron. Okay, so we'll keep that way. Basically now you can see that there are two protons. It is a helium atom and it is not stable. Yes, to stabilize it, what do we need? We need neutron. Yes, it is not a stable atom. So let's say we don't know how many neutron atoms we would need to stabilize it. We would need to add neutron. Yes, it is a stable atom. This is not the normal helium that we know. This is helium 3. Okay, not helium 4. Helium 4 is the most abundant, but this is a stable helium. Yeah, if we add another one, it becomes more stable. So now we got helium. You can also say, you know, helium 4, yeah, mass number and net charge. Okay, we can just expand that. Alright, so is this understood how the helium is formed from hydrogen? Okay, so if we add one more proton, what do you think, which element do you think from this periodic table, which element do you think is going to be formed if we add one proton and one electron? Exactly, very good. Impressed. Alright, and you can see that when you add the electron, it goes into the next orbit. What did change when we went from hydrogen to helium? What happened? We went back. Yes, we went back. So we basically now went down from hydrogen to helium, and now the electrons goes into the next orbit. Yes. Let's so again this is unstable. All right, so let's stabilize it. How do we stabilize it? By adding protons, sorry, adding neutrons. Obviously this is lithium 6. This is an isomer of lithium. It is stable, but lithium 7 is the most stable. Okay, exactly. So lithium 6 is also stable, but lithium 7 is the most stable. And so under these circumstances you can see that lithium 7 is the abundant form. When you say lithium, you actually mean lithium 7. Okay, if you mean lithium 6, you will have to say lithium 6. All right, so lithium, um, what do you think happen now if we add one more proton electron pair? Beryllium, very good, beryllium. So we do, beryllium. Yeah, we form beryllium, and we got barium. Again, the issue is that it is not stable. To stabilize it, so the idea is that the protons decide which element you are forming. Okay, neutrons decide the stability of it. All right, so we add beryllium and it is stable. Beryllium is beryllium 8, no issues. Sorry, beryllium 9, 7, 8, and 9. Is beryllium 10 more stable, or beryllium? Um, yeah, so beryllium, you can't determine, Sneha. Yeah, there is no way you can determine. This is the data. Yeah, this is basically the abundance of when you look at the periodic table, you look at the element. That's how you know that element is more stable. Okay, there is no formula for determining. Maybe there is, I'm not sure. But I don't think there is a formula to determine which atom is, or which isotope is more stable. We know that this is acquired information, basically, accumulated information. We just know that. All right, so now you can see if we add one more, let's say, proton electron pair. Yeah, we what are we gonna get? We're gonna get this: scandium, titanium, zinc, aluminium, boron, carbon. What are we gonna get? Boron. Yes, we're gonna get boron. So let's do that. We add boron, and to stabilize that, you can see that we add one more electron. It is going into the next orbit. You can see that in the first row we had two elements. We had one orbit which could accommodate only two electrons. Okay, in the second row, how many elements you have? Lithium, beryllium, 3, 4, 5, 6, 7, and 8. There are total 8 elements. How many electrons we can add into the orbital? We should be able to add 8 electrons in the second orbital. Yes, cool. So let's do that. So we got boron. Boron 10 is the most stable. You can say that we didn't even need to add neutron. Yes, we didn't even need to add neutron when we formed boron. So we simply added one. So this is boron, this is beryllium, and simply added just a proton and electron. We got boron. Okay, next we got carbon. Okay, again we stabilize it by adding, so this is carbon 12, this is the most stable. You can also form carbon 13, again stable. Carbon 14, again slightly unstable. Yeah, but it does exist. In fact, carbon 13 is the most stable isomer of carbon. So let's add, so this is carbon 13, we need to form carbon 12. Add nitrogen, so we got nitrogen now. Add electron. Yeah, we add neutron to stabilize it. Nitrogen 14 is the most stable. Okay, and again here you can see that, from the formula, there are 7 protons, 7 neutrons, and therefore the atomic mass is 14. The mass is 14, it's neutral. All right, Next one is oxygen. So you form oxygen, um, and stabilize it. Oxygen 16. Again, you can see that 8 protons, 8 neutrons, and therefore the atomic number is 16, and it is a stable atom. Yeah. Next element is again, you see that it goes to the is fluorine. We need to stabilize it. Not stable. We need another one, and fluorine is stable. Okay. 19 is the mass number for fluorine. It so it now you just need to add one more. So one more, there is only space for one more electron there. Yeah. And we get, oops, yeah, so that's, you get neon. Yeah, and we need, so it's already stable. Yeah, neon is already stable. Yeah, it's a neon 20. That's the symbol for it. Now there is no more electrons, there is no more space to add electrons into the outermost orbit, but you can add more electrons into the you can add more protons and neutrons into the nucleus, but you can't add electrons into this orbit. So let's say if we had, we don't actually have more protons and electrons, but let's say if we had more protons and neutrons, which element would be the next element to form? You would form sodium. Okay. Which orbit, in which orbit you're gonna add the electrons if you form sodium? Third orbit. So let me ask you, if we have cesium, cesium is this particular element. Okay. If we have cesium, how many orbits cesium have? 6 orbits. Okay. Maximum there are 7 orbits. We have cesium. Okay. How many orbits bromine have? That is correct. It has 4 orbits. Yeah. Vedant, Jacob, that is correct. So you have 4 orbits. How about gold, Au? How many orbits? Correct, 6. Yeah. So depending upon the position of the periodic table, you can determine how many electrons it has, how many protons it has. Okay. You can determine how many orbits it has. Yep, that is correct. It is different in the cloud model. So you can see this is the cloud model, and you learn about the cloud model because this is a simplified version of it. The cloud model, you need to understand the quantum theory. Yeah, so this is for 12th, sorry, 11th actually. Now let me ask you this one question. If we go from, let's say, lithium to sodium, which one have larger size? Which one have, okay, larger size, lithium or sodium? Sodium, right? Because lithium has only one orbit. So lithium had only 2 orbits. Sodium would have 3 orbits. Yeah, correct. Lithium this is, so this is, you can simply make lithium and just take out all the electrons. Oops. So that's lithium. Beryllium. That's lithium. Yeah, whatever. Yeah, lithium 7. That's lithium. And sodium would have another orbit essentially. So definitely sodium is much larger. Okay, what about potassium? Is the size going to increase? Rubidium is going to be even more larger. Cesium is even going to be much more larger. Francium is going to be much more larger. Yeah, so as you go down, the size increases in periodic table. So if you go from top to bottom, the size increases. Okay, so that is in general. Not all the elements follow that trend. There are certain exceptions, obviously, but in general, if you go from top to bottom, the size increases. What happens if you go from, let's say, lithium to boron? Okay, so this is the lithium. Okay, to make boron, we need to add. So lithium has 3 protons. Okay, and 3 electrons. Yeah, the neutrons are there for stability. They are basically, you can say, gas. So we add 2 more protons and 2 more electrons. What do you think is going to happen to the size? Is it going to increase or decrease? Okay, very good answer. As expected, I was expecting that answer. Um, the size, you see that we are adding the electrons when you go from lithium to beryllium to boron to carbon to nitrogen, oxygen, fluorine. We did that. We added the electron into the same orbit. Yeah. So technically, the size should not increase. Yeah, we are not adding into the next orbit. We are adding into the same orbit. So technically, size should not orbit. But when you do that, when you go from lithium to beryllium, boron, carbon, so on and so forth, you are also adding nuclear charge. You are adding more protons. Yes. What does protons do? Protons have a positive charge. New electrons have a negative charge. What should happen? The attractive force, should it increase or decrease? As you add more electrons and more protons, as you go from left to right, the attractive force between the protons and the electrons, it actually should increase, right? Because you are adding more protons, and you are adding more protons, you are adding more electrons, and the attraction between this, so it's like you take a smaller magnet and larger magnet. Larger magnet will have more attractive force, correct? That is what is happening. You are adding more protons, you are adding more electrons, and they get attracted to each other very strongly. Yes, make sense? As you go from lithium to beryllium, you are adding more protons, although you are adding electrons, but you are adding the electrons into the same orbit. Yeah, the attraction between the electrons and proton increases. So what happens to this orbit is that it gets pulled in. Yes, it gets slightly pulled in. As a result of that, the size of the atom decreases. So if you go from lithium to beryllium to boron to carbon to nitrogen, the size decreases. So in this particular periodic table, except the last column, okay, don't worry about the last column, the halogen gases, you can exclude them from any reactions. In nothing major chemistry goes on with the halogen gases, but up to the halogens, up to the fluorine, you'll see that in horizontal group, yeah, these are actually called as periods. Okay, in the period, if you go from left to right, uh, the last ones, the smallest ones, are always going to be the one on the left hand side, which is fluorine, chlorine, bromine, iodine, and I forgot the name of that. Yeah, so these are going to be the smallest atoms. Is that clear? A statin, yes, a statin. Clear. I thought the symbol was AS, but it's actually AT. Is that clear? Alright, so I'm gonna close this lab. Okay, you can also play the game here, yeah, and so you can start the game, and if you start it, you can build different atoms, yeah. And so you're given what is this, and you'll have to identify, for example, you can try and um, you can answer different questions. All right, that's just to give, but try to build different atoms and see the trend in periodic table. Next one is, okay, all right, one second. I was afraid that the recorder has been paused, but I hope it's not. Oops, one second. Little adjustments. Where is the recorder? Alright, I seem to have lost my recorder. It is hiding behind that. Oops, let me get that. Okay, so there it is, and unfortunately I'm gonna need my class link though. Yeah, something is weird over there. Anyway, I think the recording is going on. Hopefully it is. Yeah. All right. So let's do another lab. This is a small lab. Um, we'll make molecules. Okay. Essentially, one second. So this is kit 1. It consists of hydrogen and oxygen, and we can make molecules using different atoms. Okay. All right. So let's take one hydrogen. All right, and we can drag another hydrogen, and what do you get? You get hydrogen molecule. Okay, so we can drag our hydrogen over here, and that becomes hydrogen. We can actually see the shape of the molecule if you click on the 3D button. Yeah, so let's say if you click on the 3D button, you can see the shape of the molecule. Yeah, you can also click on ball and stick model. This is this is not how the molecules are. Usually the molecules are little balls that are connected, by atoms, or the different atoms are connected, which are ball like. But you can also see this will give you a better picture. In fact, you'll see that there is a bond. You can see the type of bond between the two atoms. Is that clear? Okay, and we can, where is refill kit? Okay, so you can take a refill, click on the refill kit. All right, and all right, now let's take 2 hydrogen. All right, and also take 1 oxygen, and just connect these hydrogen. Okay, so now you see that you need to put the molecule in this particular block, so you just do that. All right, so you can again see the 3D model of it. Okay, so click on that, and this is the water molecule. You can see that it has a bent shape. Yes, you can see the ball and stick model basically gives you a better picture. So I recommend that you get used to the ball and stick model, because it gives you the connections between the different atoms. The white atoms are hydrogen, the red atom is oxygen, and it is connected. Both these atoms are connected by by single bonds. Okay, is that clear, guys? You guys see it? Okay, 1 second. Okay, so let's close that. um, we can go to different kits. Okay, so we can take kit 2. We can make different molecules using these kits. Okay, so you can click on larger molecules and you can make larger molecules also. So let's make simple molecule, a simple hydrocarbon, methane. You have a carbon, just bring 4 hydrogens. Okay, and you can click on it and you can see how it looks like. That's a methane molecule. It's a ball and stick model. You can see that the carbon is in the center and the 4 hydrogens are equal distance from each other. And when you do that, this 4 hydrogen needs to be equal distance from each other, because to optimize the lowest energy form, okay, or to get the lowest energy form. And this is because of that, you got, you know, you got this particular shape. This is called as tetrahedral shape. Okay, this is a tetrahedron. If you connect all the hydrogens, you get a tetrahedron. This is called as tetrahedral shape. Is that clear? Okay, let's see one more molecule and then we can be done. Let's say you have carbon and oxygen, carbon dioxide. Yeah, let's see the molecule. This is a linear molecule. Here you can see that the carbon is again in the center, and here again the bond between the two oxygen, between the carbon and oxygen, is not a single bond, it is double bond. Jacob, I'll explain that. Yeah, give me 1 second. Again, the bond between the carbon and oxygen, both is double bond. Again, you guys see that both the oxygens are equal distance from each other. Yes, that is to lower the energy. If they are close to each other, this is called as valence bond repulsion theory, that each bond would actually repel each other. And so you don't see that in all cases. So let's see the methane molecule. Okay, and let's click on ball and stick, and yeah, you can make the ethane molecule. You can make you have 2 carbons, so you can make methanes also, ethane also. um, so if you look on this particular picture, each bond is going to repel each other. Okay, so this bond is repelling each other, this bond is, and the lowest energy form in this particular conformation is this. Okay, so that is the reason why they need to be equal distance from each other to repel, and as a result, that's the shape you get. Let's 5 regions of electron density. I don't know, you need to give me a specific example. Alright, let's build ammonia, NH3. Okay, so let's say you have NH3, and you can see how the hydrogen went. Yeah, nothing on the top. So let's see the shape of the molecule. Okay, you can see that this ammonia nitrogen is in the middle, and the 3 hydrogens are apart from each other. Okay, now why do you get a shape like this? Why do you get a shape like this? Why don't you have you know, the 3 bonds equal distance from each other in this particular case? Yes, that's the question. Why don't you have 3 electrons, these 3 bonds, 3 hydrogen nitrogen bonds equal distance from each other? They are definitely not equal distance. Clearly there is a large empty space on the top. I don't know how to stop this thing from moving, but there you can see that there is a large empty space on the top, and the 3 bonds are closer to each other. They are not equal distance. Yes, exactly, yes, that is the correct answer. The reason is because nitrogen, even though it is not shown in the diagram, has a lone pair. They have 2 pairs of electrons on the top. Okay, and these are the bosses. Basically the electrons, they repel everything in, you know, they have a stronger repelling force, you can say. So they repel these hydrogen bonds. Okay, so they are the boss. They take the most space and they will repel all these nitrogen hydrogen bonds. Okay, and that is the reason why you get a shape like that. Okay, um, Sneha, your question, I don't know what that actually means. If it has regions of electron density, I don't know what that actually mean. Um, but yeah, you can make different molecules. You can always refill kit. There are different kits. You can play with different atoms, different molecules. In fact, in the quiz itself, I have asked you to build different molecules. So there are going to be two quizzes for this session. Okay, one is going to be based on theory, one is going to be based on this particular labs. Okay, any questions? No? Alright, very good. Okay.